Okay, let me just, I'll do a little bit of introduction that you gave us. Okay, well, good evening, everybody. Our speaker tonight is Dr. Donnacha O'Driscoll from Dublin, and he's a member of the sister club in Dublin, the Irish Astronomical Society. He's a scientist by profession and the general manager of the Science Foundation Ireland Research Centre Insight in UCD, University College Dublin. Although professionally he's worked in the biotechnology and data analytical sectors, his passion is astronomy and in particular lunar astronomy. So he's been an active observer of the moon for over 40 years, which I find hard to believe because he doesn't look a day over 35, and has presented many talks on the subject in that time. He established and runs the website www.themoon.ie, which is an outreach project acting as a source of information and teaching aids on all things lunar to individuals, young and old, and to various groups and schools. So we're very pleased to have with us tonight Dr. Donnacha O'Driscoll.
Okay.
It's all yours.
Thank you indeed, Paul. I hope I can justify the introduction now. And as a 56-year-old, may I say, I'm quite quite happy with the compliment at the start. I could finish now. Right. Right, folks. I'm always kind of cautious of presentations like these because I'm very well aware of the fact that most of the audience is quite attuned to the subject and usually knows a lot more than I do. So really, please look upon this talk more in light of an amateur's attempt to try and get some of the concepts of the moon that we're all familiar with, but still it's always interesting to kind of revisit and relook some of the aspects of this beautiful neighbor of ours. And also, actually based on some of Terry's comments after my last talk there, I've added a bit more observational stuff in it. Again, I am sure there's extremely competent astrophotographers in the audience, and I would never claim to be a great photographer, but I hope maybe some of my experiences and tips might in some way be of use and interest to folk. So with all the apologies for the talk out of the way, we'll get on with the talk itself. So yes, this is a talk about our nearest neighbor, the moon. The moon is a kind of an unusual object in the sense that, yes, it's very far away. Yes, only a dozen people have walked on it, and it's in a sense an alien body to the Earth. It's also something which is extremely familiar to us, as familiar as you know, any place on Earth in a way. In fact, I mean, many people won't have ever been to Australia or seen Australia or Africa or other parts of the world, but you see the moon all your life. I think it was Carl Gilbert. He was a US geologist back in the late 19th century. And he made the point that for the near side of the moon, none of it was, as he said, terra incognito, which means that there was no part of it that we hadn't seen. And even today, but particularly in the late 19th century, there was still parts of the Earth that people hadn't visually seen. So in many ways, the moon is extremely familiar to us, but there's a lot of misconceptions and a lot of unfamiliarity with it too. So I just find it a fascinating object. So I'll be looking at things like size and distance, movement, eclipses and origin in the first half. And then in the second part, we'll have a look at observation. And I really would be interested in any conversations we have afterwards, because I'm sure people here would have an awful lot of tips and good advice on how to capture various aspects of the moon. So moving on, the size of the moon. A simple thing really, but sometimes it's hard to get the element of size across to people. You can say that, well, look, the average diameter of the moon is a little under 3,500 kilometers, but it's hard to visualize 3,500 kilometers. Sometimes what helps is if you plonk the island of Ireland onto the moon, that's relatively what the size would be. And I usually find for people not familiar with astronomy, and even those who are, that visualization alone gives them a feel for, right now, this little dot up in the sky is actually that big. So it is big, but I suppose compared to the Earth, it is relatively small. If we were to flatten the Earth out, as we do with maps, you would see that it's about 510 million square kilometers. The moon superimposed on top of that is about a little under 44.5 million square kilometers. So it's less than 7.5% of the surface of the Earth. So these are little thumbprints that help give us some idea or aspect as to the scale and size of the moon. Another way of looking at the size of the moon is wondering, well, how does it compare with the rest of the solar system family? Well, for overall size, so we have the planets, and all these planets are obviously bigger than our own moon, but not bigger than all moons. So if we superimpose the moons on top of that, you'll see that a lot of people are often surprised that, for instance, Ganymede and Titan, so Ganymede, the largest moon of Jupiter, Titan, the largest of Saturn, are actually bigger than the planet Mercury. So moons aren't small by definition. It's that they orbit a primary planet. And we see our own moon. So our own moon, in just overall size, it's the 5th largest moon in the solar system. And given the amount of moons, there are hundreds. I mean, it's hard to estimate really the number of moons. It depends on where you stop your measuring at. And it's the 15th largest body in the overall solar system. So it is an important part and a substantial part. But there's another way of looking at the size of the moon, which may be more applicable to its influence. And that is, if we look at satellites' diameter as a percentage of the planet they orbit's diameter. So if we list out the top ones in the solar system, we take Mars, for instance. Mars, Phobos, which is the larger of the two moons for Mars, but as we know, Mars's moons are very small. They're so small that they're not big enough to form spheres. But the diameter of Mars's largest moon is only 0.3% of Mars's thing. So that shows you that it would have very little influence and impact on the planet itself. Looking at the next four, the next four larger ones, Uranus, 3.1% to Titania, 3.8%. Ganymede is to Jupiter. Titan, 4.4%. Triton, the second largest relationship, shall we say, 5.5%. The largest one is the Earth to the Moon, and it's a whopping 27.3%. Our moon is larger, I was going to say than a country mile, but in universal terms, that's that much. But it's so much larger as a relationship with its primary planet than any of the other moons. So it plays an interactive and active part with the planet it orbits more so than any other moon. Now, obviously, when Pluto was taken off the list, it simplified things because Karen, Pluto's moon is actually larger. It's about 30%, but that's an unusual system. So the moon is, by any measure, really an important part of the solar system family and extremely important to Earth. The next dimension then obviously is distance between the Earth and the moon. And again, you can simply say to people, well, look, here is the moon and the Earth, and that's them to scale in size. But if we were to also add in the distance between them to scale, it would look something like this. So this is how the Earth and the moon and the distance between them would look to scale. And there's really one of my my favorite photographs, which I'm going to show you, is one that NASA shot with the OSIRIS-REx probe, which is going out to some asteroids. It shows an actual single photograph with the moon and the Earth in it. Now, the moon and Earth look almost closer than my diagram here, but it's actually taken at a slight angle. So they're actually a bit further apart than the photograph would suggest. But it gives you a lovely image of the relationship between the two bodies. But again, when you say to people 384,000 kilometers or about 250,000 miles, again, it's hard, especially to some of the younger people, to try and conceive of just how long that or what distance that is. So something that I do sometimes to try and get this across is, if there was a road between the Earth and the Moon, as stupid and crazy as that is, but if there was a road of that distance and we were to drive on that road 100 kilometers an hour, or around 60 miles an hour, and we were to set off on January 1st down that road, well, taking no pit stops, keep going, we would hit it by June 10th. You'd be in bad need of a toilet break by then, definitely. But it gives you an indication that even though the moon is on our doorstep on a universe, on a kind of a galactic scale, it's still quite a distance away. So it's near but far, shall we say? And that graphic of it would take you over 5 months to drive there at the speed limit shows you that it's, still quite a distance. Now, it is slowly moving away from us. The average distance of the moon is moving away from us, because as we'll see in a slide or two, the distance of the moon changes on a monthly basis, on a daily basis, on a second by second basis, really. But the overall average distance, it is moving away from us. It's only about 4 centimeters a year, which is about the speed at which your nails grow at. So in the greater scheme of things, 4 centimeters a year doesn't seem like an awful lot when you're talking about distances of 250,000 miles. But if you were to put the galactic time clock on that, and you're talking about billions of years, then it's said that, at the time of formation, and we'll touch on this in a few minutes, the moon may have been as close as 15 or 20,000 kilometers away from us. And in time, it has drifted off. And in time, it'll drift further away to the extent where we may lose our relationship with the moon. So it's, even though it's a very small amount of movement over the scale of, billions of years, which is what we measure things in when it comes to astronomy, it is significant. So, the next thing is the phases. Now, I won't spend too much time on this because I think everyone here knows the principle of the phases. I like showing this because I spent so much bloody time putting the graphic together that I always like to use it. So here we have the moon, or the Earth. So this is spinning at a correct rate. So we've the new moon. And then we see it comes to first quarter, and we can see on the right of the screen how it looks at us. And we know that the moon is always looking the same because the side of that's facing the sun is always lit. It's just what percentage of it do we see? And then we come back to this point where we see it's not the new moon. In fact, we don't hit the new moon till this point. This is something which some people find confusing. And that is, it's the moon to travel around the circumference, or to orbit around the Earth, and the moon to go from one new moon to the next new moon are 2 different time periods. Because as the moon is orbiting around the Earth, so when we had the new moon there, that's where the sun was, the moon and the Earth, and they're in alignment. But as the moon was orbiting, so was the Earth around the sun. So now the Earth's position with the sun has changed, and now the new moon is here. So this actually gives us 2 measurements, 2 months, 2 different types of months in a way. So we have the sidereal month, which is about 27.32 solar days. So, and sidereal is with respect to distant stars. So with respect to the stars, the sun does a full loop because it'll come back to the same star again, be it full moon or third quarter, whichever point you're measuring at. But in order for it to go through all its phases, it actually has to go a longer distance. And this we call the synodic month, which is 29.53 solar days. And synodic means it's actually relating to conjunction. So because really, when you think of it, the new moon is the conjunction of the moon and the sun. So these are two different points. And sometimes I get people saying that, I read that the lunar month is 27 days and somewhere else it's 29 days. Well, this is the explanation as to why they are those different periods. Another point as well is that it's actually not that correct to say that the moon simply orbits the Earth, because in a sense, the moon and the Earth orbit a common point, and it's called the barycenter. Now, most orbiting bodies, most moons, the sun and the planets, they don't orbit the center of the sun. They orbit points that are away from the center. Now, the barycenter for the Earth-Moon system is about 1,600 kilometers below the surface of the Earth, which is about 1,000 miles. Now, when you think of it, the Earth's radius is about 6,300. So the barycenter is about 25% between the surface of the Earth and the center of the Earth. And that's the point with which both bodies actually orbit. So if we were to look at them orbiting from above, you would see that the Earth actually wobbles around this point. And as I said, this happens for all orbiting bodies. And in fact, this is what makes, calculating orbits and effects and gravity such a complex thing, because here is the sun. And for each of the individual planets, there's separate barypoints. For the combination of the planets, there's a kind of like a combined barypoint. So, even the sun's movement is made quite complex by the planets orbiting around it. So we were talking about distance there. So with regard to movement, as we know, the orbit of the moon around the Earth, barycenter aside, is not circular, it's elliptical. So the average distance, so when we talk about distances, it's an average distance. Now, the diagram here shows an elliptical orbit, which is greatly exaggerated. If you were to look at the actual orbit of the moon around the Earth, it's nearly a circle, shall we say. It's not quite a circle, and it's certainly not as exaggerated as this, but I put this in just to kind of make the point that, it is an ellipse rather than a circle. So there are 2 points in an ellipse. And for those mathematically minded, an ellipse has 2 focal points. Like a circle is an ellipse where both focal points are at the same point and they're all the same distance from the focal point. In an ellipse, there's 2, and the Earth is at one of them, which means that there is a point with which the moon will be furthest from us, and that's called the apogee. And then there's the point where it's closest to us, the perigee. And even the perigee and the apogee vary from month to month. They're not always the same value, but these are the average perigees and apogees. And the moon does actually look different. It has between the perigee and the apogee, not so much that you would notice it at the time, because it's just the one moon. You can't see the moon, the perigee and an apogee side by side. But if you could, you'd see differences. Now, one thing I should say here is that lunar phase and lunar distance are unrelated. People often talk incorrectly about, well, the full moon. Obviously, the gravitational effect of the full moon is far greater than the new moon. But that's not true at all, because the point of perigee and apogee and where the moon is on the elliptical path when it's full are unrelated. It can be, for instance, here's a simple diagram. So here, the blue line shows the orbit of the Earth around the sun. And each black line, so we've looked at the Earth at different points on this orbit. So we can see then the moon's orbit at each of these points. Now, on each occasion, the moon, it's a full moon, but we can see that on each occasion, it's on a totally different part of the ellipse. Sometimes it's at perigee, sometimes apogee, and more often than not, it's some point in between. So this thing that the full moon is somehow has a greater gravitational pull on the Earth or is near the Earth is an incorrect assumption. But if the full moon happens to occur at the point of perigee, then we refer to it as a supermoon. And if it happens to be at the point of apogee when it's the full moon, we call it a micromoon. And if you could somehow put the two together, if you could standardize your photographs and compare them, you would see that a supermoon is about 14% bigger than a micromoon and is about 30% brighter. Now, as I said, it's hard for people to pick up on this because you're seeing them individually, but there is a significant difference there at the same time. But that's your super and your micromoon. Now, on this whistle-stop tour of the moon, we hit eclipses. Now, I would love to give a talk on any of the slides I've given today and would happily do so. So these are very, very just overview, brief looks. So as we know, eclipses are based on the fact that the moon gets in the way of the sun for the Earth at times. And you can see here where an eclipse occurs on the Earth, a lunar eclipse, a solar eclipse. And we can see that the way the shadow forms, it's a very small shadow on the overall surface of the Earth. So therefore, it's a very limited space where a solar eclipse can be viewed. And you have to be in that particular location, and you only get it for a few minutes to see a solar eclipse. So it's a rare event that a solar eclipse would happen anywhere near you. I certainly plan to get over to the States in 2024, where 2024, where it promises to be quite nice. And of course, there's a solar eclipse promised much closer to home in the following year, which will cross Iceland and the north of Spain. And of course, then we have the occasion where the Earth shadow affects the full moon. And so this is a lunar eclipse. And because of the setup here, anyone who can see the moon during a lunar eclipse will experience it. So we have all seen lunar eclipses on a number of occasions, and it's a much more frequent event. So that's the standard, and that's easy and straightforward. But something I always get asked by some people when who might be familiar with the dynamics here is that, well, why aren't we getting a solar eclipse every month and a lunar eclipse every month? Because you just shown in your previous slide how the moon goes around the Earth in between the sun. So they're in each other's way each month. Well, the first thing we need to do to explain why is, so this is the Earth's orbital path around the sun. And then we have what's called the orbital plane. So that's effectively, if you can imagine like a flat disk, the edge of that disk is the orbit of the Earth around the sun, and the center of the disk is the sun itself. And we also have the orbit of the moon and the moon's orbital plane. Now, usually when we depict moon, Earth, and sun, it's from above. So when the moon orbits around the Earth, we see that it goes between the Earth and the sun. When you look at it at the side, the orbital plane of the moon is at about a 5-degree angle to the orbital plane of the Earth about the sun. And this then has an effect as to how the moon's and Earth's shadows interfere or interact with each other. So, as we said, when you have a new moon or a full moon and the Earth shadow, we get, as we said in the previous slide, we get the solar and lunar eclipses. But on the occasion, which is most occasions, when the moon is, as we say, between the Earth and the sun, it's actually between but above or below, because that angle there can tip below, and you can see then that the shadows actually miss each other. Both the shadow of the moon during the full moon period misses the Earth. So that's why we usually don't get a lunar or a solar eclipse or a lunar eclipse every month. And this, so it's unfavorable for an eclipse. And this, in fact, the vast majority of times that the moon is between the Earth and sun, and Earth between sun and moon, this is the occasion. The tilt of the two orbital planes are at an angle, and therefore the shadows miss their mark, so to speak. However, as you'll see, the planes do cut each other. They have to cut each other. And if at the time of full moon, I'm sorry, just showing here that the paths of the moon, Earth, and sun are not in straight lines, they're in crooked lines. But if it so happens that the full moon or the new moon, depending on which we're looking at, happens to intersect or be at the point of intersection where the lunar orbital plane and the Earth's orbital plane intersect each other. So if we get the full moon just at that point, then we're favorable for an eclipse. And this happens, there are patterns because it doesn't happen on a regular basis. And quite often, as you know, you can get patterns where you might have 2 solar eclipses in a year and none the next year. So it does work itself out in a pattern. So this really explains why we don't get eclipses, unfortunately, every month. And I'm sure everyone is aware of the fact too as well that eclipses are a pure freak of nature. There is no law or rule in nature to say that we should have eclipses. No other planet in the solar system has eclipses like we have, because by a freakish coincidence, the moon is about 400 times narrower than the sun, but it happens to be about 400 times nearer to us. So from our perspective, the sun and moon appear to be the same size, but like there's no rhyme or reason. There's no reason why that had to be the case. And it's the only place in the solar system where when you stand on your planet that any of your satellites and the sun appear to be the same. So during a full eclipse of the sun, and you see the corona around the sun, and you can't see the corona normally because the sun itself is too bright, that's the only time in the entire solar system where the corona can be seen naturally. So it is an interesting phenomenon. And as I said, the moon sometimes is closer to us. So sometimes if it's smaller, as we said, like a micro moon, it's not big enough to cover the sun. And we get what's known then as an annular eclipse, where there's still sun seen around it. So it is a fascinating a coincidence, and an amazing and a brilliant one, because it gives us such a lovely spectacle. Right, the giant impact hypothesis. So the last bit before looking at some of the observation stuff is, how did the moon form? Now, there's been a long history as to theories as to where the moon came from and how it formed. There were many theories, including, and really up until the 1960s and 70s, there was quite a bit of scientific debate and competition, you might say, between certain theories, like co-formation. So as you know, about 5 billion years ago, you had, when the sun was forming, and you had this cloud of particles orbiting around the sun, and then particles would start to stick to each other, and their gravity would increase because they were slightly bigger, and then they'd attract more particles and more. And so you get these bodies forming. The term is called accretion. And so that's how the planets formed. And then smaller planets would crash into each other and form bigger planets. And soon all the bits were kind of hoovered up and you were left with the present planet systems. And one theory was that, well, the moon formed at the same time and happened to stick with the Earth and go around. There were other ones. There was ones whereby you had kind of a straightforward fission process where during an early stage, it just kind of disconnected from the Earth. There was all different theories, but one of the great things about the Apollo program, apart from man going on the moon, that's the romantic side of it, and it's brilliant, and I'm really looking forward to it happening again. But there was a very strong scientific side of it as well. And the rocks that were brought back from the moon really strengthened the impact theory. And the impact theory is basically that about 4.5 billion years ago, the proto-Earth. So you had this accretion system happening. So you had this Earth, as we call it, the proto-Earth, and you had another Mars-sized planet that had also been forming. But as I said, you had multiple planets, far more than we have today, forming. But eventually, because there were so many in gravitational attraction, some were going to collide with each other. So it's believed that a Mars-sized planet, and they've given it the name Theia, so it collided with the proto-Earth, and it's called the proto-Earth because it's only after this collision can we say that this is the Earth as we know it today. So the two, they didn't vaporize each other. What happened was that there was a tremendous explosion. They pulverized each other in a way, but the gravitational pull of the proto-Earth was so strong that it was enough to keep the colliding particles together. And so what happened was the two formed a new planet, the Earth as we know it today, with residual mantle being thrown off. This mantle then formed a circle around the Earth, pretty much like the rings around Saturn. And over time, these particles in the rings coalesced, accreted like the Earth was formed, till you got the moon. Now, some of the arguments for this is that if this theory is true, then the moon's iron center proportionally should be much smaller than the Earth. And in fact, it is. And the reason being is that, as you can see in the proto-Earth, that red dot there are the heavier elements. And a lot of them had gone to the center of the Earth before this collision. So when you had jettison of material, a lot of the lighter stuff was thrown off, but a far less proportion of the heavier, which means that the moon has a much smaller iron core than the Earth has, which explains how it moves. And that's correct. But also the nature of the rocks should have a huge amount in common with the Earth because it basically came from the Earth, and it does. So they've looked at a lot of the structure, and a lot of the study of the moon rock show that much of the chemistry is very similar to that of the Earth. Now, that's a very kind of a dry way of looking at it. Hopefully, now we did test out this video beforehand. The BBC did a nice little 60-second video, which I think more dramatically gets across what happens here. So here we have the proto-Earth accreting. The particles increasing in size. So eventually, about 4.5 billion years ago, it was this large body. And it started to cool for the cooling process. Here it comes in, and there's the collision. And it's hard to imagine the scale of this explosion. It was phenomenal. Now, obviously, there was no one around to hear it, but it was phenomenal. And you can see the ejecta here, and much of it would be the outer parts of proto-Earth rather than the inner parts. Here was thrown off. There then you had it completely. Obviously, we're talking millions and millions of years here, all condensed down into a few seconds. And here you have moonrise. Now, this part of it is really interesting because this looks like an exaggerated version of how big the moon might look. But remember, I was saying that the moon is away from the Earth at about 4 centimeters a year. It's actually, that movement might be slowing down at the moment. So what the part that I like about this video is this, that the Earth, or the moon may have been maybe only 20,000 kilometers away from the Earth at the start. So it was this huge body in the sky. Again, there was no one there to admire it and be in awe of it, but it must have been some sight. Observation, and the last, I'm okay for time, about 10 minutes on observation, sorry.
Absolutely fine.
Great. So the first thing about the moon, as I say to a lot of people, is, just looking at it as is with the naked eye, leaving telescopes aside, and we'll look at the telescopic side of it. And really, it's free to view once the clouds aren't there. And I know that's a big if in Ireland. So I think it's just a thing of beauty that you look in the sky, and even to take out your phone and photograph it. And like, we take this picture here and you enlarge it. And like, for me, science aside, and, the astronomy facts and figures aside, just looking at something like that and contemplating it, it really gives you a sense that we are floating in space, because there is another huge spherical body floating out there right beside us. And, no matter how many diagrams you see, or books or pictures or talks like this, when you go out and actually see the moon like that, to me, I think it's fantastic. And I try and hope that, people get an appreciation of just how, beautiful it is, something which we sometimes maybe just take for granted. Earthshine, I mean, that's something that you can appreciate even with a simple, camera phone or with the naked eye. It's very hard to pick up even with a camera or a camera phone. So here we have the moon, and you can see some features there, not a lot, but you can see some of the shadow relief. If I increase the exposure, which I did here of the shot, you start to see the rest of the moon. And what I did here now was I just overexposed, and you can see here then basically the rest of the moon. In fact, you can make out the slight shapes of the various seas on it. So the moon is there, it hasn't disappeared. And that's, as we know, is Earthshine. There are the ashen light, as it's called. So as we know, we see brightness on the moon because sunshine is deflected or reflected, I should say, from the moon down to the earth. So that's moonshine. But we also have Earthshine, where sunlight bounces off the earth and hits the moon. That then bounces back to us because obviously for us to see it. So it's greatly decreased, but we do get to see it very slightly, but we have to overexpose a photograph here. Now, the lunar albedo measurement is 0.12 and the Earth is 0.3. What that means is the albedo is the measure of how reflective a surface is. Now, 0.12 means that the moon reflects about 12% of the light that shines on it. The Earth reflects 30%. So the Earth is far more reflective than the moon is. So on the moon, full Earth is about 50 times brighter to look at than the full moon is when you stand on the Earth. So in fact, the moon, even though it looks quite bright in the sky, is actually quite a dull surface when you compare it to the other planetary surfaces. Most of the planets, Uranus, Neptune, Saturn, Jupiter, they all got an albedo of about 0.3 to 0.35. Venus being the exception, it's got 0.75. Venus actually reflects 75% of the light that shines on it. That's because of the dense CO2 cloud around it. The moon and actually Mercury as well. And the reason why they've got such a low albedo is that they have no atmosphere. So there's no, in a sense, an atmosphere offers almost like a flat surface for light to bounce off. But the moon and Mercury and some of the other moons, the light is actually bouncing off the rough terrain, you might say. And so rather than it bouncing straight back, it gets dispersed left and right, more so than it would if it was hitting an atmosphere. So that there is why we get to see Earthshine. Now, there is actually quite a lot to see with the naked eye. And if you look at the full moon, after a while, now I like actually looking at the full moon and seeing if I can identify, features, and you can. And, for those who've never looked or spent a while just looking with the naked eye, there is quite a number of things you can see. Now, here I have labeled all the seas, but most definitely we'll say the Sea of Serenity and Tranquility and the Sea of Crisis and I suppose Fertility are relatively easy to see with the naked eye on a good full moon. And they always look to me more like someone running up to a football with the Sea of Crisis being the ball. And also, if you get familiar with those shapes with the naked eye, you can then tell people, well, look, that's near where Apollo 11 landed. So you can actually roughly work out where the Apollo 11, where we first walked on the moon. It's not some just general spot somewhere on the moon. You can actually localize it with the naked eye to see where it happened. So there's quite a lot to be seen with the naked eye. And I mean, I love looking down the telescope, and we'll talk about it now, but I always encourage people as well just to look up and see, even the stars and the moon and the planets. So there's a lot there to be seen on naked eye. Briefly on telescopes. Now, I'm going to apologize for the next slide because it's me getting out of soapbox. It's a thing that annoys me a lot. And so I might as well inflict my annoyance on ye. In medicine, if you had an offer of someone examining you with the stethoscope on the top or the stethoscope on the bottom, you would laugh and say, well, for God's sakes, that's a piece of equipment and the one below is a toy. It's standard practice. One wouldn't sell equipment as toys. And it's the same. You can get, toy hammers and toy this, that, and the other, and real ones. For some reason, many shops and reputable shops seem to think that it's okay to sell what are evidently toy telescopes as real telescopes. And what annoys me is that unfortunately, you get a lot of young people buying these, finding what they look at is, excuse my language, but it's just crap, and they lose interest. And I really think certain outlets should be brought to task, or there should be some signs saying that they're toys. Because this is a photograph I took a few weeks ago. In fact, I took it for a talk I did there about 2 weeks ago. And it's in a very well-known store that's in Britain and Ireland, and they're selling this telescope. Now, it's for €65, which is about 56 sterling. And they're making claims that, use this telescope and you will see, the planets, and you'll see the moons of Jupiter and see the craters on the moon. There's a few things that is obvious that this is not a real telescope. One is the price. Really, you're not going to get anything that's worth using in a shop for about that price. Minimum 100 to 200 euros. I think you should be spending a bit more than that. But there are some, Celestron and Orion have some good entry-level telescopes for around £100. So they are good. But really, at this price level, that should be your first flag. It's not a definitive one. You never know. You might get a good value of a second-hand scope, definitely. But it mostly, if that's the price. Now, the next thing is this. Codology. On the box, they describe it as a 700 millimeter telescope. Now, we know that when you look up about telescopes, when they talk about an X millimeter telescope, they're talking about the objective lens, but they're putting 700 millimeter telescope, but it's actually the focal length. It's nothing to do with the objective lens. So it's a kind of like a misdirect. I would say at most, I couldn't see it on the box and I wasn't going to get it. It's at most maybe, I don't know, it looks like a 3-inch, maybe 700 millimeters, maybe a 3-inch scope. And you can be fairly sure that in a lot of these cheap scopes, they have, they've a stop, like a thick rim around it. So it's actually maybe 2 inches, maybe at best. And of course, they love talking in these things about magnification, not the objective lens. They should. The fact that they're not talking about the objective lens is a red flag. Light capture, as you know, and lens quality is the all-important thing. Magnification, if anyone sees in the box, it means nothing. I know that doesn't seem correct because people would say, well, look, a telescope is all about magnification. Magnification is a simple process. You can get any lens and magnify an image as much as you like. You can make it 1,000 magnification if you want. But as you know, if you have an object and if you magnify it 10 times, it's going to be about 100 times dimmer than it was before you magnify it. So obviously, the brighter that object is, that's what will dictate how much you can magnify it, not what lenses you're using. They will let you magnify it more. But all you'll get is this faint smudge. And also, if the lens qualities aren't good, no matter how many times you magnify it, you still get smudge. In fact, as you know, a good quality telescope, maximum magnification would be about 20 times per centimeter of the objective lens, or about 50 times per inch. And that's at the limit of a good scope. So this scope, even if it had very good lenses, which it doesn't, at max, maybe 150, it's advertising 525 magnification. I think that if there was any other product being sold as a serious item with that amount of misinformation on it, they would be had up, but it seems to be acceptable. Sorry, I will now get off my hobby horse because I'm sure you've, but this most definitely, and of course the cheap mount, won't even get into that, is a toy. Right, now with my rant over, very briefly, what I use for a lot of my photography is a Celestron 5-inch. I have an 8-inch, but I usually use the 5-inch. And the SCT our Smith-Cascarian telescope, for the Schmidt-Cascarian telescope, as you know, is in a sense like a collapsed telescope where it folds, you're able to fold the light and thus get a smaller length tube for a longer focal length. So it obviously, it's a very popular scope because it makes it quite portable. Now, I would recommend personally as well, before ever doing photography, use an eyepiece. Look at it. Some of my friends have got good telescopes, and the first thing they do really is they try and put a camera on it before they ever start looking through it. Spend time looking through it and appreciating what you're seeing. But then when you want to do photography, now I use a Skyris 274 CCD. It's not a very high quality one, but for a lot of the lunar stuff, it's more than ample. So I slot that in where you would normally put the eyepiece. I have a dedicated small cheap PC with freeware, really. It's an image capture software. And so then you can either take a single image, or you can, what we say, take a stack image. So, you know, you can program these things and it will, in a few seconds, take a load of images. And well, with image one, you can optimize it, vary the exposure, the contrast, you know, to get the most out of it. With the other one, you can use, there's a lot of freeware or paidware. This is a fairly standard, the Starry Sky Stacker. So what that does is it takes all the images, plants them together, and optimizes, takes the best ones and optimizes them to give you the best picture you can. So that's the kind of photography I do. It's fairly low key. Now, that package is about €1,800, but you don't have to spend that kind of money at all. You know, you can use your iPhone, you can have a cheaper telescope, but even in the scale of things, 1,800, if you're really passionate about it, isn't a huge amount of money either, not being flippant about cash, I guess. So the Terminator, this is the part of the moon that we really all chase when we're trying to get details. Because as you know, a full moon, I mean, there's a lot of features to see in a full moon, but it is a relatively boring surface in one respect because there's little or no shadow. And as we know, it's shadow that gives form to the 3D features on the moon. So the Terminator, which sounds something from a movie, as you know, is the line just between the dark phase and the light phase of the moon, because that's where the sun is most angled and we get shadows thrown up from every feature that's on the surface. So here's a photograph I took on the Terminator, and I really do like I like chains of craters. So here you have 4 craters, lovely looking features, and you can see they range in size from 41 to 153 kilometers. And you can see them quite clearly and quite distinct. If you were looking at them on a full moon, you would not see the walls, the central peak, and they'd look quite flat. So that means that your opportunity to see certain features, you have to schedule it and hope the night is clear, because they come and go in hours, as we'll see in the next slide. Now, just one thing that I'm interested in is the age of craters. And I won't get into it now, but there are 6 kind of ages that craters are classified into. An eon is 1 billion years. So, and they're fairly broad spectrum. But you can see here that each of these 4 craters come from different ages. So there's a whole history behind one going on top of the other, we're going on top of the other, and even on the mare. So that you can tell a lot about how the moon formed, when it formed, just by looking at the pattern of craters and when and how they formed. Another interesting thing is the peak. And I love this thing. You can imagine you have a central peak here in Arzachel, and it's about a mile high central peak. It's huge. And because the gravity is so low on the moon, you can get features which are far higher and smaller than you would get on the Earth, whose gravity would tend to pull things down. So the peaks usually form by, if you can, you know, when you drop a stone into water and you get the stone plunging in and the water kind of gloops up. It's kind of like a reaction to the pressure of the stone going down, and the water presses up and it causes the water to rise. And of course, then with water, it flattens out. But with the rock, the impact is so violent when a meteorite impacts onto the surface, it liquefies the rock and it acts like a liquid. And so you get this gloop or drop coming up, but it will actually solidify quite quickly. So it actually freezes that way. So you get these lovely peaks in the middle of these things. So these are all the little features you can see just by looking at shadows on the moon. My favorite, if I was to pick a favorite place, it would be Clavius. Now, Clavius is about the second or third largest crater on the near side of the moon, depending on how you measure things. Now, it is said that you have to wait till day 8 to see it. But this just shows you, when you look at books, and for anyone who mightn't be used to, you know, observing the moon or trying to figure out using a lunar atlas when I can see certain things, day 8 is 24 hours. And that's a long time in the moon, because Clavius is actually there, and it said you can see it on day 8. Now, this is also day 8 moon, but you can see it quite clearly there. Remember, the shadow of the moon is passing across constantly on the moon. And so shadows are changing on an hourly basis. So capturing certain features and seeing certain things is a passing thing. And sometimes if you miss it, you of course have to wait, sometimes even a month, because even when the shadow's coming the other way, it looks totally different again. Now you can see here Clavius, it's a beautiful crater. It has some of the largest walls of any crater on the moon. As I said, it's one of the largest ones. So it's about 232 kilometers. Because it's so far south, we're actually seeing it at an angle. It's bigger if you were to look at it face on. And the walls are about 3.6 kilometers. That's over 2 miles high. I mean, it must, to walk in this crater must be phenomenal. And you have this beautiful curve of craters that obviously occurred afterwards in it, and is a different age. So just by looking at shadows on the moon, you see all these features and you get to know so much. So it's really, I'm sounding a bit nerdy now, but you see all these beautiful things, and not just seeing features, but you can get so much information and knowledge about the moon from them. My final slide on just nearly my final slide of the talk, identifying features. One of my favorite photographs that I took a few years ago is this photograph. And there are some features on the moon which are, many people say, of course, that's an obvious one, but I'm a slow learner. If you look at this and you look, now I was going to label the photograph for you, but I got lazy, and I have a moon app that gives the label. So you see all the features here and they're amazing. But right here where the square is, at first I thought I'd maybe a hair on the lens, or there's some scratch or something that caused that bit of a line, but that's actually a true feature, and it's called the straight wall. And you can see it's right beside the Bert crater. Now, so I like trying to take detailed photographs of this. Now, this is actually what we call an escarpment. Escarpment, I'm missing an N there. I'm sorry, that should be ENS, escarpment. Now, what that basically is it's not a wall. Actually, what it is if this was, the blue square here is a cross section down through the surface of the moon, and you can get fault lines like you do in Earth. You can get fault lines forming on the moon, and then part of the ground collapses. So that's what's happened here. We have a fault line all the way along, and they tend to be relatively straight. So you can see the escarpment there. And in fact, it's not actually that steep. There's a mild slope on that. The diagram overstates how steep it is. But you can see also to the left another feature. Now, it looks similar, but it looks a lot more crooked. But this is called a rill. And the reason why it's a lot more crooked is it's something different altogether. Now, how we believe rills formed is, again, if we were to take a cross section, remember we had a lot of volcanic activity on the moon, in the past. And because of the lack of weathering, a lot of the effects of the volcanic activity still exist. So if you can imagine, this red circle represents a cross section through a stream of lava flowing along the surface. Now, the lava flows very slowly, and it's a big, thick piece of lava. Now, the outside of it will start to cool, while the inside of it is still hot and liquefied. So what happens after a while is the outside starts to cool and harden, and eventually the outside crust stops flowing while the inside still flows. and you're left basically with like a tunnel. And over time, that tunnel can collapse, leaving this kind of trough. And that's what this rill is the remains of one of those troughs. So again, just by looking at shadows through your telescope, you get to see features and kind of evidence of the history of the formation of the moon, which again, I find fascinating. Listen, that's it. If there's more information you'd like to see, please do visit my site, themoon.ie. There is downloadable talks, diagrams. I do videos. It's all for free. It's an outreach. Please pass it on to anyone who might be interested. The reason why I do this and these talks is just to try and instill interest in the moon and in science in general. And so with that, all I can say is...
That's all, folks.
And that's it. Sorry, I overran there, I'm afraid, but hopefully didn't bore people too much.
Donnacha, that was absolutely fantastic. Actually, in less than an hour.
Oh, sorry, I had thought I'd get it done in 45 minutes, but okay.
Very interesting. Very interesting. Thank you very much.
Really a fantastic amount of information and beautifully presented as well. So that you've covered some quite difficult concepts in a way that's really. I do a lot of this sort of outreach stuff myself, and I'm not near your standard yet in terms of conveying that amount of information.
I see there's comments there, Paul. Do we go through?
Do you want to take a few questions?
Yeah, sure. If I just
run through the chat and see what we've got there.
Yeah. So yes, I see Terry. They're talking about the dark side of the moon. Now it's a phrase I may use, but of course, just to be absolutely sure, when we talk about the dark side of the moon, that's a transient characteristic, because obviously all sides of the moon experience as much daylight and as much dark time as any other side. A lunar day, as we know, is about 2 weeks. Now, people do sometimes refer to the far side of the unseen side of the moon as the dark side, but of course that's incorrect, because when we see the new moon and it's dark, it is, you might say, a full moon worth of light on the far side. So just in case anyone picks up on that, it's incorrect to call any side of the moon the dark side in a permanent way. So fair point.
Exactly, yeah. And the first question I'll start with there. Now, with the moon slowly moving away from Earth, will this cause sea levels to rise?
Yeah, so some things I cut out of the talk, as Terry will probably have picked up, and I did talk about the effect on oceans and waves and gravity, but I want to spend a little bit more time in observation this time. But it will, absolutely. Now, humans, I should say, is doing a damn good job in changing the sea levels themselves without the effects of the moon. But yes, there will be effects. However, we still have to say that on the scale of human life, this is a long way away. So, by the time the moon moves far away to have a significant change to its gravitational fluxes, who knows, how life would be on Earth. So it will, in theory, yes, but nothing that we will experience or see in millions of years. So, it's nothing I'd get worried about on that aspect of it. Yeah.
Yeah, brilliant. Now Terry did pick up on a point here that I don't think you quite covered very much, but that was when explaining that there's no dark side as such, and we understand that.
Yes, and that's where I was picking up on Terry's point.
We can on occasions see a little bit of the far side, yes?
Yes, and I was going to put that in, Terry, and I found, as you saw, I couldn't even squeeze in the stuff I should squeeze in. So absolutely. So obviously, at any one time, we only get to see 50% of the moon at any one time. But if you were to combine all the moon that you can see over a length or over a period of time, we can see probably about 60% of it. And it's called libration. And the basic thing is that, as I showed you there, the orbit of the moon around the Earth and the Earth around the sun, it's quite a complex thing. The angles change, our angles are the same. So even though the same side of the moon is always facing us, because of the speed of movement of the moon, the change of angles, it's not always quite the same angle. So there are parts of the edges of the moon that you can see sometimes, and other parts will disappear. So if you could imagine the moon wobbling side to side and up and down this way. Now, it's not so much, now the moon does wobble a bit, but wobble is the term we would use for libration, but it's not so much that the moon itself is wobbling, it's that our perspective of it is changing relative to us. So, and in fact, one of the great things for lunar observers, and kind of it's the train spotting side of it, is trying to see features that can only be seen at times of maximum libration. And sometimes if you miss it, you have to wait a long time to see them again. I don't know if Terry would like to give word to that, but it's another, obviously, aspect of observation.
Well, actually, I'll say something about that, because the image behind you, actually, Mare Crisium is right close to the edge there, closer than the average, and therefore the opposite side of that, you could probably see teeny bits of Mare Orientale just becoming apparent. But so that's a libration sort of that's fairly favourable for that. Did you see the exhibition that goes around places where they've got a sort of a, I think it's wrong to call it a blow up, but a model of the moon. Yeah,
indeed. I actually saw it, believe it or not, when it was in Cork about 3-4 years ago. It's magnificent, it really is.
And of course, that's got an accurate depiction of all the bits you can't see as well.
Yes,
Mare Orientale is absolutely fantastic on that.
Oh, absolutely. And I said it at the last talk as well. Of course, an awful lot of the moon, and at some stage, I'd love to talk about the lunar program, the Apollo and the Artemis programs, and even the social and political side of it, because one of the big seas that were discovered, the biggest one on the far side of the moon, is named after Moscow. And of course, there's a lot of controversy about this, because it's that the naming of the moon, of the features of the moon, was never to be politicized. But Russia claimed, because it was their probe that first photographed it, that Moscow is a representative of a state of mind. And everyone said, okay, we leave it, but that it's a political eyesore in one respect on the far side of the moon. Just a little thing.
Absolutely, yeah. Terry picked up your point about telescopes, and I would agree with that. I have a rule of thumb about telescopes, actually.
Yes.
That reinforces what you're saying. Is that the better the pictures on the box, the worse the telescope usually.
Yeah, probably. Yeah. It's as good a rule of thumb as any. Yeah, absolutely.
But Terry was saying that was probably what you're looking at. There was really, by the time you take into account the probable stop down in it, probably only a 50 or 60 millimeter.
Oh yeah.
Lens there, but
and even the 50 millimeters you're left with isn't that much anyway. They're going to be plastic lenses. They're non-couplets and chromatic. It's even describing the quality of them, I think, is giving them more respect than they deserve. It's a plastic toy.
You manage the expectations of people and say, well, you will see through this maybe craters on the moon and the 4 moons of Jupiter, and that'd be a lot, pretty much.
And even at that, what's really bad about them, I should say, is the mounting. Yes. They have terrible mounts. Yes. It means that anytime your eye even touches off it, everything dances around the place. So I see no redeeming features with and I suppose it seems unfair that, well, look, someone is trying, they're at least buying a telescope for their child, but you'd be better off buying a pair of binoculars. And they get far more joy out of it.
Sorry, I'm grossly underrated.
Yeah, absolutely. I'm very militant. Sorry about it.
Excellent. Let me just have a scroll down here, see if there are any other points there that something's there. That's a superb talk. Thanks. Well, it was indeed.
Good.
And we enjoyed it as we did. What is the mechanism which makes the same side of the moon face the Earth all the time?
Okay, so I mean, as you know, it's so the term used is called tidal lock, and it often happens when you have a smaller body orbiting. So I didn't do the wave thing today, but basically, if you think of it, the moon pulls the surface water of the Earth towards it, so you get this bulging of the Earth in a sense. Now, it might be small, but it's a significant bulge. this bulge actually gives almost like a gravitational lens effect to the pull of the moon. So as the moon is going around and its relationship, it causes the moon to actually be pulled a bit, and it slows down the orbit of the moon. So originally when the moon formed, it did spin on its own axis independently of its orbit. But the moon and the gravitational pull from the Earth and this bulging effect of the water, it caused like a drag on the, like a gravitational drag as the moon rotated, causing it to slow down till eventually it slowed down right to the same period of time that it was, you might say it was locked. It no longer turned in relation to its orbit. Now, the moon obviously does orbit. It orbits once a month. Like if you were to look at the moon on its own and kept the Earth out of it, you would see that it would rotate. But its rotation now is locked to the Earth because of that gravitational drag. And because of that, then we only get to see one side of the moon the whole time. I don't know if that describes it.
Yes, that sounds right. And also, of course, the reverse is true, isn't it? That process is happening much more slowly in the other direction, that the Earth is slowing down as a result of having the moon.
That's absolutely true. And I mean, like the Earth's day, we say going back a few million years, well, a couple 100 million years, might have been 27, 28 or 29 hours. So the moon itself is having a drag effect on it also is, for instance, and I'd love to give a talk sometime on how the moon actually shaped life on Earth. And that's not an exaggeration, because the moon, for instance, helps maintain the Earth's spin axis angle, which is, that our axis is at an angle, which gives us the seasons, which has a huge effect on life on Earth. Also, they believe that, for instance, the tidal motions that the moon causes may have been a key factor in actually the formation of initial life on Earth. So, it has a huge, huge effect on Earth. We wouldn't have been here but for the moon. So,